Hello, everyone. I am Tianying from storage caching team in Pinterest. Today, I'm going to talk about a story of HBase upgrade at Pinterest. So today, I will first talk about the HBase usage in the Pinterest. Then I'm going to talk about the challenges we face to upgrade from HBase 94 to 1.2 with zero downtime. And the next, I'm going to talk about detail how we solve the challenge, how we do the live cluster upgrade. And then we'll talk about the performance tuning we did. So HBase at Pinterest. In Pinterest, we start to use HBase around 2012. And the very first application is actually the Pinterest home feed. So originally, the Pinterest home feed was hosted by the Redis. But due to the concern of the cost of those memory boxes and also the reliability, availability, we decided to try some storage that has better persistent. That's why the HBase was picked. So eventually, Pinterest home feed is moved to HBase, and it turned out a good result. After that, the search and discovery team decided to try HBase also. So their particular use case is their key, for example, is a ping ID, and the value is a list of related pings. This is for their related ping features. So after this couple first initial successes, we start to wonder, can we actually provide a general store in front of the HBase so that the application developer, they can actually focus on their product development instead of learning the internal of HBase? So that's how the user meta store was born. The user meta store basically is a general store layer that provides a list of general key value type of API, for example, get and put. So any application has this key value type can actually use it. And particularly, the very first onboarding use case for us is just like the name as stated. It is actually save the Pinterest user's meta profile information. So originally, they are stored in MySQL, and they are stored as a big JSON blob. So as you can see, it's very hard to retrieve or get a particular field of this user metadata. But once you switch to HBase, because of flexible schemaless, all those different fields can be actually stored as a column. So it's convenient, flexible, and performant. So once the user meta store roll out to production, there are more and more other type of key value applications start to use this. So it is a big success also. So after that, we want to think like, can we extend even more? Because not all applications actually can fit into the key value type of use case. So particularly, lots of applications actually can be better modeled as a graph service. For example, in Pinterest, the ping or the board that containing all the pings, or the Pinterest user, they can be modeled as a node. And for example, if the ping contained in particular boards, or if a user following another user or following another topic, they can be modeled as an edge. So with that thought, that's how the Zen, a graph service on top of HBase, was born. So then the use case of HBase flourished after Zen was released to production cluster. So besides the general Zen and UMS we also have other miscellaneous use cases. Particularly, we use HBase for analytics. We're also using OpenTSP for our internal company's metric system. So that brings us to, like, we have eventually 40 plus HBase clusters in Pinterest, and they are all on version 94. So HBase 94 is not supported by the community anymore, about like 2 years ago. And the newer version, claim has better reliability, availability, performance, and so on. So it's good if you can upgrade. And also, it will be much easier for us to contribute back to the community. We're motivated to do that, but on the deprecated version, it definitely make it harder and also less incentive. Well, as many of you may already know, the singularity of HBase. Basically, since the version 94, many changes has been made to HBase, many actually breaking changes. For example, the RPC protocol has changed from the Hadoop writable to the RPC, the protocol buff. And also the data format has changed, HDF folder structure has changed, and API has changed, and so on. So generally, with all those changes, it is considered almost impossible to do a live upgrade with zero downtime. Well, here's a dilemma. on one side, the singularity said you cannot live upgrade from HBase 94 to a later version. You have to take downtime. But on the other side, since Pinterest already used HBase to host so many critical online-facing real-time services, we just cannot afford downtime. We cannot take Pinterest offsite home feed like downside just because we're upgrading HBase. So are we stuck? Well, let's fast forward to a happy news. So eventually, we successfully upgraded the production cluster last year. And we choose actually one of the most loaded cluster as a pilot cluster. The reason is obviously we have 40 plus clusters. If we can get the most loaded cluster successfully upgraded with good performance, it will be pretty confident that the rest of lighter loaded cluster can be upgraded easily. But it will not be true the other direction. And on the day of switching, there is no application redeployment or the application restart even needed. So it's completely zero downtime. And the live switch did not cause any interrupt to Pinterest site. And even better, we actually get a big performance boost. Here is a peek at the performance. So here it shows the P99 latency of different Zen level API. This graph service I talked about earlier. So you can see at the point of a switch, the latency for all the API actually dropped at that point. So now let's talk about how did we do it. Before I talk about how we upgraded from 94 to 1.2 with zero downtime, I want to first talk about how we operate HBase cluster in Pinterest in general. So normally when people use HBase cluster, they have a client, they have single HBase cluster. The client will read and write to there. And obviously, if this cluster has any performance issue, the client will be impacted. You will have latency impacted, you have availability impacted. But since Pinterest is rely on HBase for online services, this is not accepted by us. So in Pinterest, almost all online-facing services are actually supported by a pair of clusters. They are supported by master-master replication. So clients still talk to one of the main clusters, read and write there, we call it master. But all the updates also be replicated to the other cluster, we call it the slave. And if something goes wrong on the current master cluster, we can quickly just tell the client to switch to another cluster because it has almost the same data except with a little bit replication lag. And then we have high availability and low latency. After we switch, then we can take a look at the original master cluster and either fix it or do the maintenance. So we're doing this for many, so we have 40 plus clusters, and we're doing it for many of them. So we actually have a set of tools to automate this process. That is part of the DR tool. I'm not going to talk, but just talking about the subset we're using here. So here, particularly, you start with a single cluster with a client and with tables in it. Now our tools will kick in. Well, first, the tool will build an empty HBase cluster. That's very easy. And next, we'll set up the replication. And obviously, the replication will not flow at this moment because the new cluster has zero table. So the updates will be held at the master cluster at the replication queue. And next, our tool will take a snapshot of all the tables and then export them out to the new cluster. Once the export is done, the tool will recover the table from the snapshot. Once the table is recovered, the replication starts to drain. We'll wait for the replication to drain, and then we get a pair of clusters have exact same data. At this moment, the client has a freedom to switch back and forth whenever they need it. We use this process not only to bring up a bootstrap a production cluster, we also use it to set up a test cluster that has the same production data for our testing purpose. Since we're using it so often, it's just very natural and intuitive for us to think, can we actually do the upgrade with a similar process? The only change is now we're switch between two different versions, right? So if we can just do this, then upgrade is done. Right? It's very easy. So now let's revisit what problem we need to solve if we want to reuse this process. So first, we start the same with a one cluster scenario. And then first the tool will kick in to build a cluster, the same, nothing changed. And next, we'll set up the replication, the same. But please note, because of the RPC protocol change, the native replication cannot be used anymore. So that is the first major problem we actually need to solve. And next, we need to export snapshot. This is exactly the same as what we normally do for the 94 clusters. So nothing need to be changed. And next, we need to recover a 1.2 cluster, 1.2 table from a 94 snapshot. So here is also the slight change we need to make. Similarly, we'll wait for the replication to drain, and after the replication is drained, the client is free to switch to talk to the new cluster. And please note, here is also the problem we need to solve, because now the client switched to a different HBase. So it need to be able to talk to the new version with no downtime, with no redeployment. Okay, so now you're probably clear the major problem that we need to solve here. The first is the client has to be able to talk to both 94 and 1.2 automatically. They can switch back and forth. There's no redeployment or no restarting needed. Second, the data has to be able to flow between 94 and 1.2 bidirectional. So why do we need bidirectional? I'll talk a little bit in a few minutes. So the first is the client-side problem. Well, in Pinterest, instead of using the native synchronous HBase client, we actually choose to use the third-party async HBase client. The reason is the async actually has better throughput and latency. We did some tests before we choose this, and turned out to be for the exact same load. The async HBase actually only use half of the CPU, while at the same time actually can cut the latency to half. So that's the reason. And then another side benefit we got, we didn't know about when we choose this, is actually the choosing async-based client make this no downtime switch easier, because the newer version, the async HBase 1.7, they actually can talk to both 94 and the later version, because it can detect the HBase version and then use different protocols. But the life is not that easy. We cannot just directly use the stock async client 1.7. The reason is we actually made many private improvements internally. And those need to be, so we actually have to work to make those private features to work with 1.2 cluster also. So here is the list of improvement we made to the async HBase client. So first, the batch get, or you can call it multi-get. Basically, given a list of get requests, the async client will actually regroup them based on the final destination region server. And then for each subgroup, it will be sent to the destination region server with only one RPC call. So we measured that the batch get actually has better lower latency and use less CPU compared with when you are actually sending the exact same list get requests in parallel, but with a single get. And this improvement is especially bigger once you have bigger batch size. One interesting thing I want to mention is the batch get feature was actually listed as one of the most popular requested feature in last year HBaseCon for the async HBase talk. So afterwards, we talked to the owner, and then we just open sourced it quickly. The next feature is the small scan. So in HBase, normally the scan involves at least 3 RPC. First, you send open scanner, and then you could call the next row, 1 or more, depending how much data you have. And in last, you call close the scanner. So it works for us in generally fine, no problem. But then one day we start to get page saying that some region server get high CPU and latency was slow. And we take a look at the log and also the stack trace and find lots of this scanner timeout, and also shows this locking back and forth. So then we decide we want to implement the small scan feature in to see how it helps. So basically, small scan just merge the 3 RPC into 1 RPC. And also at the HBase server side, they did optimization that get rid of this redundant locking. So after we get the small scan into the async base and deploy the production cluster, we do not receive that page duty anymore. And then the ping feature. So we use AWS Amazon environment. What we find is sometimes the connection just become very weird. There's no data going on, but there's nothing else shows anything wrong. So to solve that problem, we actually add this proactive ping. When those kind of things happened, we'd use that to detect if something wrong and then reset a connection. So pluggable metric framework. Well, async RACE has many metrics. However, they're not exposed very well. We want those async-based metrics can be exposed to our company-wide stats board, so that whenever there's a site issue, we actually can look from async HBase client side to see what goes on. So that's why we build this pluggable metric framework with Juice. So basically, you can implement your own pluggable version based on your company's stats collector. So for us, we implemented the ostrich version, so that all those async pages now show side by side on the company's the dashboard. We also add metrics that's broken down by per RPC and per region server into the async base. So it is very useful for debugging issues with better slice and dice. For example, from the metrics, we see the latency to particular region is high, and we can see which RPC is causing it. And then the on-call people can actually go back and then manually throttle or blacklist the client requests that are causing this problem. Well, however, this is still not good enough, because the on-call people starts to page, and then the human intervention has to be done. Then there'll be a delay of say 10 or 15 minutes to get the site recovered. So eventually, we made further improvements that can automatically rate limiting, basically throttle blacklist the request based on certain metrics. For example, if the latency to a particular region become high, the async base will automatically, throttle or blacklist any requests that go into that region. So that will help the hot region to come down to help it to recover. Once the latency drop down to normal, then the async will allow the client request to flow again. So you can never prevent the bad user, either it's malicious, intentional, or just like naive mistake. But you can prevent them from a better layer. From our experience, it is much better place and also much easier to do it at async RIPS layer than if you want to try to do at HBase region server side. It's already just too late. So all these features are in progress to be open sourced also. So now the client side is solved. Let's look at the server side. So question is, how can we live migrate all the data from 94 to 1.2? This problem can actually be break down to two smaller problems. First is you need to export a snapshot from 94 and then recover them in 1.2. So this is a relatively easy problem because we are already doing it between 94 and 94, and we just need to modify our existing DR backup tool to take consideration of the new HDFS structure of 1.2 and make the corresponding changes and then recover the snapshot. But now is, after the snapshot is taken, how you ship the updates that made since the snapshot is taken. So obviously you cannot use the native replication anymore. Well, the answer is we use a thrift replication to overcome this issue. Okay. So the thrift replication. So we actually got a private patch from Flurry. They have the fix for 94 and 98. When took it and made some change and applied to our cluster, it works well in general. But we did find a bug. So basically, it is a threading bug that exposed during the production data testing when it's actually under the high red QPS. We fixed it by implementing a thrift client connection pool for each connection sync, replication sync. And the fix actually also shows better latency, basically made the replication faster. So bidirectional. So I mentioned we need bidirectional. So why? So you just need to migrate from 94 to 1.2, right? So the reason is when you're doing a live production data upgrade, no matter how much preparation you have done, it could always possible that you miss something, some hidden bug, you just show up. So you feel much better if you can fail over if that kind of thing happens. So if the replication now can actually do bidirection, that means once you switch to 1.2, all the write go into 1.2, but then the data also replicate over back to 94. So you have a 94 cluster that has same copy. So if something wrong in the 1.2, we can just easily switch back to 94. The site is not impacted. And at the same time, we can investigate and debug, see what is wrong, fix them, and switch back. So with this ability, it's just much comfortable, much confident we can do the switch. Verification. So because the thrift verification hasn't been used much by other people, so we want to make sure the data is 100% correct. So we built a tool called the checker that is used to check the data, has the consistency from 94 to 112 or from 112 to 94. And because we need to verify the live update, we actually add a configurable timestamp that can eliminate the false positive caused by the replication delay. So now all the problem, client side or server side, has been solved. Now let me recap the upgrade steps we can do in our production cluster. So first, we will build a new 1.2 empty cluster. And then we set up the master thrift replication between the 94 and the 1.2. And next, we export a snapshot from the 94 into 1.2, and then recover table in 1.2, and you wait for the replication to drain. After that, you just want to monitor the health a little bit, make sure nothing else goes wrong. And when you're sure everything is okay, you can switch your client to use the 1.2 cluster. So one thing I want to mention is you probably want to choose a good day to do your switch. You probably don't want to pick like Friday afternoon to do your switch, no matter how confident you are. Cool. Okay, performance. So because we are using the HBase to host our online-facing real-time applications, so the performance is as important as the functional issues we have solved. We cannot at least degrade the performance after we upgrade to 1.2 cluster. So in our company, we actually use the production dark read-write traffic to verify the performance. So we actually set up the side-by-side comparison during the performance test. So on one side, we have a 94 cluster that taking the production traffic from the business site. On the other side, we set up a 1.2 cluster, but it's taking the dark read-write traffic into this 1.2 cluster. So the two cluster has exact same traffic at the same time. And then we compare the round-trip latency measured from the async HBase layer. The reason we use this is first, although the 1.2 has the P99 server-side latency, but the 94 doesn't. And second, we also believe that it's actually a more complete picture if you're measuring the latency from client side. That's really impact what the client can suffer. So fortunately, we already exposed those metrics breakdown by RPC region in the async bits and exposed them in the ostrich. So it's very easy for us to see those metrics on the dashboard. So here is the performance breakdown by the 5 major API in the async HBase client. So there's get, batch get, put, compare set, and delete. Wow, this is really hard to see, I guess, the picture. So on each, if you can see it, so on each API, basically, it's so, I don't know, the color is just so bad. It's actually the top line is supposed to be green. That's for the older system, and the bottom line is like orange color. So I can see from my side, but basically the latency has been dropped consistently for all the API. Okay. So now talk about the read latency. So when we first turn on the dark read-write traffic with the default configuration, we're actually surprised to find that it has worse P99 latency, basically long tail latency. After some digging, it turned out to be the off-heap bucket cache is the problem. It's actually hurting our long tail latency. It is because in the 1.x version, the implementation actually has to copy the data from the off-heap in. And also, even if you only need to read a small byte, you have to copy the whole bucket chunk into the heap memory. So that actually causes lots of garbage. And we are very sensitive to garbage collection because we care about this P99 long latency. So after we turn it off, the rate latency actually become better. But if your use case are, for example, you need more memory and you don't really care the long tail latency, it's probably actually working for you. But for our use case, it just doesn't. And a couple other things I want to mention is, say, the short circuit rate helps latency. The native checksum helps latency also. And for the garbage collection, we still use CMS instead of G1GC. We were actually very excited, want to try the G1GC when last year they were released some good performance on the G1GC. However, after we apply those configuration, it turned out to be, it doesn't meet our SLA. For us, we need the P99 latency to be at least lower than 100 millisecond or 50 millisecond. But the G1GC can only reach like 300 millisecond. So we have to give up that and still use the older CMS garbage collection. And next, I want to mention the write performance. There's one interesting thing we find. So we use the write heavy load, try to expose the potential performance issue. And we did find actually the write latency is actually worse than the 94 beginning. And eventually find actually one of the metrics is the wall sync operation metrics actually shows that in the newer version, it has much higher wall sync operation. It's like over 1,000 per second. It's completely unnecessary. Basically, the disruptor-based wall sync implementation causes too much wall sync operations. So anti-intuitively, we actually tune down the thread handler count from the default 5 actually down to 1. And that helped to reduce the wall sync operation a lot, therefore improved write latency a lot also. So that's the kind of surprise we find. And in the last, I want to thank the community for all the helps we got. And particularly, I want to shout out to Michael from Cloudera and Raul from the Flurry. So Michael gave us a lot of valuable feedback and advice. We do the performance tuning, and Raul gave us their private patch. Okay, so now we're hiring. So any questions?
Okay, time for just a couple questions.
You talk about the smaller scanner to reduce the 3 RPC to 1 RPC. Can you talk a little bit more on that?
Yeah, so the small scan actually already featured in the synchronous native HBase. So they actually did improvement by merging the RPC and also the server-side change. But the async-based client, because they don't have lots of resources, so they don't actually have the feature in. So we basically implement that features into async-based and then take advantage of this.
What kind of changes did you make when you were importing data from 0.94 to 1.2?
Can you say again? What
kind of, you said like you guys have made change in the data recovery and backup process in order to import the data into 1.2 cluster.
You mean
the data snapshot?
Yeah.
What kind of changes did you make to import so that we'll be able to import into 1.2 cluster?
Oh, you mean the step that we kind of recover a 1.2 table from the 94 snapshots?
Yes.
Oh yeah, so it's basically, exporting the snapshot is actually same. So you export a snapshot with the same structure as 94, but that's not recognizable by 1.2. So we basically did like some HDFS, level, made some files that recognizable by the 1.2 and move the file to the correct folder and stuff like that. Sorry.
Did you convert into 1.2 H file format so that we can load it onto 1.2 cluster?
Because it's actually the H file v2 actually is recognizable by both, so you don't have to do that.
Okay.
So basically just folder structure, the snapshot versus table, that it's actually will not be recognized, it will fail if you don't make those changes. Okay. But file format is supported by both.
Okay.
Because we use H file v2, so.
Thank you.
All right, thank you very much.